Okay, cool. So I'm going to be talking more about actually programming these GPUs. So we've seen a lot about like the history and how we use them, but maybe we can get into more of the programming aspects of these GPUs. So to start off, I want to introduce this program you've probably all seen in 217, this Hello World program. So it does exactly what you would expect. It just prints Hello World to the screen. To compile this program, we use GCC, and it outputs exactly as you would expect. And I guess the question here is, what kind of changes do we have to make so that we can actually run this program on the GPU? And it turns out that we actually don't have to make that many changes. So this is the GPU version of the code, and we'll talk through the various aspects of it. But to compile the code, we use NVCC, and the output is pretty much what you would expect as in the CPU program. And then just for reference, all of the code is in a GitHub repo, so you can access it afterwards. And then I'll denote on the slide where you can find it. So the first step, like the first main difference you might notice is this global keyword. And to really understand what this means, I'm going to introduce some terminology. So in GPU programming, we call the CPU the host, because the CPU is kind of the orchestrator, as Professor Martinosi put it, that orchestrates like when we call the GPU, how to read in the data, stuff like that. And then this GPU is then called the device, and the kernel is the function that has to run on the device. So we call the kernel from the CPU code, and then it starts running on the GPU. And this is, the kernel has to have a void return type, because there's not really a place for it to return the value. So if you did want the kernel to actually return a value, you want to have like an out parameter, but we'll see that in an example later. And then because GPUs are these massively high throughput devices and CPUs are maybe less high throughput, we want to program with both. And this paradigm of programming with both is called heterogeneous computing. It just means that we're using a number of different processors and to get like a task done. So then the global keyword is used to modify a function that basically runs on the device, is called from the host code, and it denotes the kernel. So in this example on the left, hello kernel is the kernel. It's the code that will start running on the GPU. It's called within the main function of the CUDA program. So that's why it's called from the host code, and we call it the kernel. There are a number of other qualifiers, including host and device, and they just specify other like runs on and called from combinations. And by default, if you don't have any qualifier, it just means that it runs on the host and is called from the host. Another difference you might notice is this weird triple angle bracket syntax. And this is actually used to denote a kernel launch. So we saw a little bit of a GPU earlier, but basically it's, when we launch a kernel, we have this grid of blocks, and then we have a block of threads. So there are two parameters to this triple angle bracket notation. The first parameter is the number of blocks in the grid. So in this diagram here, we have 8 blocks in this grid, because there are 8 like gray squares. And then the second parameter, m, is the number of threads per block that you have. So here, I believe it's also 8, because in each of these gray blocks, we have 8 little arrows, which denote threads. And then the total number of threads then is just the product of these two numbers. So in this example, we're launching 1 times 1, so 1 thread, which is not very interesting. But you can think of the kernel launch as similar to a C function call. So the main difference is that instead of a function call that runs on the CPU, the kernel runs on the GPU. And when we actually launch the kernel, we have n by m threads running the same code all in parallel. And to kind of better understand why we have these two parameters, I'm going to talk a little bit about single instruction multiple thread, which is the kind of architecture that CUDA uses or CUDA implements. So basically, the idea is that all the threads in the same block are assigned to a streaming multiprocessor at the same time. So if you look on the screen, this combination of streaming multiprocessors, that's a GPU. And we have multiple streaming multiprocessors within a GPU. And the idea is when we launch a kernel, all the threads within the block get assigned to the same streaming multiprocessor. And this will help with coordination. And some other subnotes, a block is not assigned until it has all the resources it needs to execute. And because there are limited memory resources on a GPU, we limit the number of threads per block. It's 1024 on a lot of modern GPUs. And then the unit of scheduling within a GPU is actually called a warp. So this is 32 threads within the block. So instead of each thread running its own separate thing, we coordinate in these units called warps. So basically, all 32 threads execute the same instruction at the same time. Each thread, though, has its own program counter, register state, and can have an independent execution path. So what this means is if your kernel has like an if and else branch, some threads in the warp might go down the if branch, some might go down the else branch, and that's completely fine. And then even deeper, within a thread, we can have instruction level parallelism, which we kind of discussed in a lot of the previous lectures. So here's how we would launch a grid with 32 threads per block and one block. So we just changed the second parameter to 32, and what it would do is it would print hello world 32 times. We can also change the value of the first parameter, so now we're launching 4 blocks of 32 threads each, and this would print 4 by 32, which is 128 hello worlds to the screen. And the last difference, or one of the last differences you might notice, is this call to CUDA device synchronize. And the idea here is that unlike a C function call, kernel launches are asynchronous. So I guess how many of you have programmed with P threads before? Okay, maybe not. But in P threads, we have this idea of P thread join, which means once we launch a thread, we have to wait for the thread to do its work, and then we can continue on with whatever work the main thread was trying to do. So the idea here is very similar. So as soon as we launch the kernel, so this call in line 8, as soon as that call completes, the control immediately returns to the CPU. So we launch one thread on the GPU and have it run hello world, but then immediately after, the CPU can continue running whatever's on line 9. So if we didn't have this call to CUDA device synchronize, then what do you think would go wrong? Yeah. Yeah, exactly. So you can have some race conditions and non-determinism, which is not so fun to debug. But the idea is that you might have the kernel running its own thing, but then if you move on without the kernel finishing and you try to like read some results, then the results might be like half complete or not complete at all. And in this case, you might see hello world in some cases, but not in others. And then finally, I wanted to talk briefly about the compiler. So MVCC is the compiler driver, and what that means is it just separates the source file into the host code and the device code. So we talked a little bit about the qualifiers before, and basically it looks at these qualifiers and decides, should this like function be compiled on the system's C++ or C compiler, so like GCC or Clang, or should this be compiled by NVIDIA's device compiler? And basically, if it's compiled on the device, it's packaged into what is called a FAT binary, and then later embedded into the host object file and then linked so that you can have a final program that has both the CPU and the GPU components. And then here's a fun diagram from NVIDIA's documentation. But now I wanted to talk a little bit about the programming model. So you saw this diagram earlier, so I'm just gonna jump through this. But basically, because the GPU does not have access to CPU memory or disk or any of that, the main workflow that we follow when we program a CUDA program is we allocate memory on the device, and then we copy everything all the input data over to the device. And then we call the kernel using this data. And then once we finish running the kernel, whatever we want on the GPU, then we copy the results back to the CPU. And as you'd imagine, the communication between the host and device can be really slow, especially if you're copying like gigabytes worth of data over. So basically, the idea is you want to try to limit copying whenever you can. So if you can just copy everything in one fell swoop, then that usually works better than trying to copy individual things multiple times. And then to actually do this copying, I talked about this earlier, but the host and device memory are separate. So the device pointers point to GPU memory, and you can't dereference them on the CPU. Similarly, the host pointers point to CPU memory and can't be dereferenced on the device. And you might be thinking, like, why can't we just have one big page table that tells the CPU where to find the GPU's memory, and et cetera? But if you think back to our discussion on page tables, remember that we can have like 2 to the 48, for example, virtual addresses, and that would be a huge page table. And if you need to manage this for every single time you want to access GPU memory, this is like prohibitively large. So kind of the solution to that is just to copy this data back and forth. And then CUDA offers an API to do this memory management. So the API consists of the functions you see on the left in the table. They're very similar to what you would expect when you're programming in C. So to allocate memory on the device, we have CUDA malloc. To transfer data between the host and device, there's CUDA memcopy. And there's a fourth parameter in this memcopy function that maybe looks unfamiliar, but this is just to specify what direction you want to copy the data in. So you can copy data from the host to the host, or you can just use the built-in C memcopy for that. But the more interesting ones are trying to copy between the host and the device, so host to device and device to host. And then there's also a default that just infers the direction you want to copy in based on where the pointers are actually pointing. And then finally, to free memory on the device, there's a CUDA free function. And you might notice that a lot of these, or all of these functions return CUDA error T type, which is basically an error code that if it's CUDA success, that means whatever you tried to do was successful, which is good. But if it's anything other than CUDA success, then you can actually use CUDA get error string, which is like a built-in function to check where the error kind of stemmed from. And the error can come from 2 places. It can come from the API call itself. So for example, maybe you're calling CUDA free to a pointer that doesn't exist. Then the call to CUDA free would raise an error. But also, if you're trying to launch a kernel, remember those are asynchronous. So those return to the CPU immediately. If there was an error in that, then the CUDA error code for the next thing you try to do on the GPU will also raise an error. And then unlike kernel launches, these functions are synchronous. So if I'm doing a memcopy from host to device, I don't have to call synchronize because memcopy will not return until all the data I want to copy from the host to device is copied. So we've looked at a Hello World program, which is perhaps not very interesting. I think the canonical example for programming a GPU is vector addition. So say we have a very, very large vector. Here it's like 16,000 by 16,000. And we want to basically compute the element-wise sum of each entry within n-dimensional vectors A and B and store them in some other resulting vector C. And you might notice that all of these sums can be done basically in parallel, right? The sum for index 1 does not depend on the sum for index 100. So why not just have 2 separate threads do that? So that is the idea of trying to offload this program to a GPU. And what we want to be able to do is assign each GPU thread so that it's responsible for some index. But then the question becomes, how do we determine this index? Any ideas? Well, I guess it's like hard to know if you've never programmed in CUDA, but just thinking back to the thread hierarchy. So we have this block of threads and this grid of blocks, right? And it turns out that CUDA actually has built-in variables that allow you to access the index within this block of threads or within this grid. So block IDX is the variable you would use to access the block ID within the grid. And thread IDX is the variable you would use to access the thread ID within the block. And then these are actually both three-dimensional. So in this image, it's two-dimensional, and in the examples in the code that I've shown previously, it was one-dimensional. But you can imagine that basically there's a y and z dimension as well. Here we're just saying it's 1, and the y and z index is always 0, just for simplicity. So we have these block IDs and thread IDs, and now let's look at an example where we have maybe just 24 entries that we want to compute the vector sum for. So we can launch a kernel with 3 blocks and 8 threads per block. And this is kind of what the setup would look like. So each of the different colors denotes a different block. Each of the different blocks has a different block ID. So I guess it's not hard to see that maybe we want index 0 to be worked on by thread 0, and block 0 is just a matching from here to here. Similarly, index 1 should be worked on by the thread at index 1 in block 0. So on and so forth. Index 8 should be worked on by thread 0 in block 1. That's this one here. And then I guess if you looked at this long enough, you can come up with a general formula where the index is just the block ID, so the value here, times the dimension, the number of items within the block, so here's 8, plus some offset into that block, which is given by the thread ID. So we'll use this formula to kind of assign work. So this is the beginning of a vector add kernel, or this is the vector add kernel. But basically, the way you write a kernel is you just peel off the for loop. And because all the threads kind of start running at the exact same time with just different values of block ID and thread ID. So if these threads are all running in parallel, then we can just have them compute different IDs and then work on that specific index. And then here we're computing the ID in line 2, and then we're saying if your ID is within the size of this array that we want to add, then do some work. If your ID happens to be greater, then it's your lucky day, you don't do anything for this function. And then how would we call this kernel? So first we want to just allocate memory for the host. I'm ignoring the allocation for B and C just for simplicity, but you would do the same thing for B and C. And then we want to allocate the device memory. So this is where our call to CUDA malloc comes in. We call CUDA malloc, we pass a pointer to the pointer we want the address to be written to. So here it's DA. DA is the version of A that is on the device. And then after we call CUDA malloc for B and C as well, we can mem copy the results or the inputs of A and B over to the device versions so that now we have the copy of the input on the device. And then once we have everything on the device, then we can actually run the function, call the kernel. So this is how we would launch the kernel. We would have to pick some number of threads per block. And once we know the number of threads per block that we want, the number of blocks that we actually want to launch would just be basically n divided by the threads per block, and then we want to round up so that there's, like, every index is accounted for by some thread, and there might be some leftover if it's not a perfect multiple. Once we launch the kernel, then we want to call synchronize because otherwise we run the add kernel and it's possible it doesn't finish and we try to mem copy the results back and it won't make sense. But once it's synchronized, we can call memcopy and get the result back to host, and maybe we want to do some stuff with it before we deallocate. So any questions with like the setup here? Okay, cool. Oh, sorry.
So I just wanted to make sure, like, why are we doing n plus threads per block minus 1 divided by threads per? Can we like manually assign that, or is there a reason why it's n plus threads per block?
Yeah, so good question. So remember the first argument to this kernel launch is the number of blocks you want, right? And basically we want the total number of threads to be able to cover all of n, because there's n pieces of work that we want to do. So if each block is doing, or if each block has threads per block threads, then in order for us to have enough blocks to cover all n pieces of work we have to do, we want to round up. So this expression is basically n divided by threads per block and then doing like a ceiling.
Got it.
Yeah, this is a common way to round up. And then, yeah, there's a similar question in assignment 8. So I guess maybe the question now is, how much better did we do from the CPU version? We did a lot of work to move the data around to the GPU and maybe to do some computation, but like, was it worth it? And I guess the answer is yes. So this is the timings I got from the GPU, and the total time is basically the total time it took the program. So we can see that there is almost an order of magnitude speed up between the CPU time and the GPU time. And each of these rows within the GPU time represent a different number of threads per block. So when we use 64 threads per block, the speed up is maybe a little less than when we use 128 threads per block. And if we actually look at just the time it took to execute the kernel, there's actually like several orders of magnitude speed up. So we do see that there's a pretty massive speed up, and the reason the total time is much longer than the kernel time is because we have to copy data back and forth, and that takes a really long time. So if we can minimize the amount of data we're copying back and forth, we can take advantage of the speed up a little better. And since there are such differences between different numbers of threads per block, I guess another question might be, how do we choose like an optimal block and grid dimension? And to understand that, we kind of want to understand the execution model that CUDA uses. So recall the single instruction multiple thread architecture that we talked about earlier. Maybe some of you guys have been wondering, like, what's the point of even grouping threads into groups of 32? Like, what's the point of having warps? Because why not just let all the threads execute independently? Does anyone have any guesses? Okay, I'll give you one. So on the one hand, we have some like hardware simplicity with having 32 threads all execute the same instruction at the same time. And this actually happens to be like a micro-architectural like implementation detail. Warps are not actually built into the programming model, so there's no way for you to say, I want to use warps where there are 64 threads in this warp. It's actually like just a hardware level optimization. And the API doesn't let you kind of manage them, but it's used internally to simplify the control logic, and ultimately it improves performance. So because we have that all threads in a warp execute the same instruction, that means we only need one fetch and decode unit in each of these. So this is one streaming multiprocessor, and within the streaming multiprocessor, we have 4 different processing blocks. And basically, a warp can run on any one of these processing blocks, and the unit of scheduling on one of these processing blocks would be the warp. So each processing block only needs one fetch and decode unit I think it's built into this like L0 instruction cache and the warp scheduler in this diagram. But since everything's executing the same thing, we only need to fetch and decode once, and that's the idea. There's also an idea of memory coalescing. So all instructions will hit like a load word instruction at the same time because they're all executing the same instruction at the same time. And that means basically from all 32 threads, instead of 32 separate memory accesses, we can just combine them into larger memory accesses so we don't have to go to memory as many times because going to memory is slow. And as a consequence of this, we also need fewer load store units. We don't actually need a load store unit for each core that each thread is running on because we can coalesce these memory accesses into these larger transactions. And then there's also implicit synchronization. So because they're all executing the same instruction at the same time, we don't need to worry as much about synchronization within a warp because it's guaranteed. And what this ultimately implies is that there's more space on the chip for all of these cores and all of these compute units because there's less control logic. Like we spend a lot of time talking about like the CPU and why it has like caches and why it has all this like extra control logic, branch prediction, all that. The GPU kind of throws all of that out the window and says, we have all of these compute units for you to do all of these compute instructions in parallel because we kind of have these extra assumptions, the warp being one of them. Another benefit of having warps is this idea of latency hiding. So for example, let's say warp 0 is running on some kind of processing block, and then it hits a load word instruction, and then it can't make progress because we have to wait a few hundred cycles for to go to memory and get whatever data we need. But in the time that we're going to memory for warp 0, we can actually execute warp 1 on the processing block. If warp 1 stalls, then we can execute warp 2, and then maybe warp 0's memory comes back from memory, and we can do more work on warp 0, and so on and so forth. So this is the idea of latency hiding, which just means that we take advantage of the thread level parallelism so that the hardware is fully utilized, even if we're waiting on memory or waiting for some other thing that we're stalled for. The warp scheduler can choose what warp is executing in any given cycle. So there are 3 different states: selected, stalled, and eligible. If it's selected, that means it's actively executing. If it's eligible, that means it's ready to execute as soon as the warp scheduler puts it on. And if it's stalled, that means we're still waiting on some resources, so it's not ready to execute. So if we're stalled, then the warp scheduler can just pick another warp to run so that this warp is stalling and waiting on memory, we can put another warp on. And it turns out that most of the performance improvements that GPUs have and the massive throughput that they provide is from this latency hiding. So CPUs, we've discussed, have been designed to minimize this latency, so spend less time going to memory by having caches, for example. But here we're saying we don't care about how long it takes for you to go to memory. As long as we can keep the processor busy while we're waiting for memory, then we're good, because we get the work done in the same amount of time. Any questions? Okay, cool. So I guess maybe at this point, some of you guys have identified a contradiction, perhaps, in the way I presented this. So I did say that threads are executed in groups of 32, and that each thread executes the same instruction at the same time, but then I also said that each thread can have its own independent execution path. So what gives? Like, how is this possible? Any guesses? Or is this like truly just a contradiction? So the answer is actually a concept known as warp divergence. So the idea here is that if we have different conditional statements in the kernel, then a warp can diverge. So that means threads in the same warp are actually trying to execute different instructions. So in this example, some threads are trying to go down the if clause and the other threads are trying to go down the else. And basically in this time that the threads have diverged, the warp has to serially execute each branch path. So we talked a lot about how threads have to do the same thing at the same time. So here, if a thread is going down the if branch and we're not executing the if branch, then all those threads just do nothing in the time that we're going down the if branch. And similarly, if a thread is in the else branch and we're going down the if branch, then just wait until we execute the else branch. So this actually causes a lot of slowdown, as you'd imagine, up to 32 times, because there are 32 threads in the warp. And if we have 32 different branches, each thread going down a different branch, then we can basically serialize our entire GPU code, which kind of makes something that we want to try to avoid. So I guess, what are some solutions? Can you guys think of any solutions for this? Yeah.
I don't know if this is possible, but it looks like if we could move, sort of squeeze the grid, so whenever something's not executing, whenever something's stalling, have it do like basically vary what you're executing within each of the threads, so that you're never stalling, or you're stalling within.
Yeah, that's a good idea. And I guess just to elaborate on that, we as the programmer get to choose what blocks do what. And if you can design your blocks such that all the things in a warp go down the same path, then you don't actually ever have to stall, because everything in that warp always goes down the if branch, or everything in that warp goes down the else branch. So that's one solution. Any other ideas? Yeah. That's a good idea. So basically, so the blocks don't really have communication with one another. There's synchronization within a block, but there isn't really a way to synchronize between blocks. So I think that would work if you implemented the architecture to work that way, but for this particular model, that might not work as well. But here are some other ideas. So as one of your classmates mentioned earlier, we can partition work so that all the threads in the same warp take the same control path. Or we can try to avoid the branch altogether, and this is what we'll do in a minute. Or you can just move the if and else outside of the branch and pass them as parameters, so that ideally you do the if and else in the CPU code, and then when you actually go to the GPU kernel, everything in that warp is doing the same thing. So now I wanted to move on to the demo. Basically here I've written a bunch of different diverging kernels. Okay. I've written a bunch of different diverging kernels. So this div kernel 1 has no divergence, so everything does the same. All the threads in the warp do the same thing. Div kernel 2 has half the threads do x plus 1, and half the threads just do x. Work is just kind of a contrived example of trying to do a lot of compute. Compute sine times cosine. And then we have div kernel 8, where there are 8 different branches depending on the warp's, the thread's ID, and then 16 and 32. So I guess, does anyone have any guesses on what the run times will look like? Any guesses? Oh. Okay, I'll show you if there are no guesses. So let's try to run this. So when we have one branch, it takes 0.09 seconds to run the code. run the kernel. When we have 2 branches, it takes 0.17 seconds, so almost double the time. If we look at 32 branches, it actually takes almost 32x time. And the reason for this is just because we're serially executing all the different branches. So we end up with a lot of serialization in our code. And I guess here's the 32 branch code. It's very, like, can you guys think of a way to improve this so that we don't have 32 branches? So we're performing a switch on the lane, and the lane is a number between 0 and 31, and we're adding it to x.
Can we just use index and put there's 31 cases, we were setting 31, so we could just say run in for that number to each index.
Yeah, exactly. So I've done like, oh, Copilot. So this is the answer. Basically, you can just always add the lane so that every single thread in the warp actually just runs x plus lane, but every single thread in the warp has a different lane. But this will execute in parallel because there are no branches. So I've called this div kernel 32 improved. And we can run it to kind of get a sense for the improvement. So the first few take the same amount of time. But then now with the improved kernel, we actually see that it does better than the kernel with only 1 branch, with no divergence. So I guess the lesson here is that you want to avoid divergence whenever possible. And one way you can do that is just try to get rid of branches. But yeah, so I guess I asked earlier how we choose this block and grid dimensions. So the answer is it depends on your system, on your hardware, on your workload. But some tips, I guess, for choosing these values. So you want the GPU to always be kept busy. There's a lot of streaming multiprocessors, and there's a lot of processing blocks that can do work on different warps. So if you have a lot of warps to actually like switch between, then you can always keep it busy. So the idea is you want to avoid small block sizes. If you have large block sizes, then you can always have something that should be operating or should be executing. And then you want the number of threads per block to be a multiple of warp size, so you don't actually end up with threads that are doing nothing. And this is kind of a concept of occupancy. And then there's always ways to profile your code so that you can choose something optimal. But yeah, there's a number of topics that I didn't get to or that I did not have time to get to. So in case you're interested, here's a list. And then you can see the demo code at this GitHub repo. But yeah, remember to fill out the ICQ. Thank you.